An ice age is coming, and it's not Milankovic who says it, but glaciers are retreating, Greenland is blooming with flowers, Arctic ice is disappearing, sea levels are rising. Stop global warming, or the Earth will die. This, more or less, is the relentless message we've been bombarded with daily for years. Everyone says it, so why shouldn't we believe it? Only a few persist in claiming that the anthropogenic origin of global warming is merely an unproven conjecture, deduced solely from complex computer programs known as general circulation models. On the contrary, scientific literature has increasingly highlighted the presence of natural climate variability that these models fail to reproduce. This natural variability explains a significant portion of the global warming observed since 1850. The anthropogenic responsibility for the observed climate change in the last century is therefore unjustifiably exaggerated, and the catastrophic predictions are unrealistic. The climate is the most complex system on our planet, requiring appropriate and coherent approaches commensurate with its level of complexity. According to the minority of climate change skeptics, climate simulation models do not reproduce the observed natural climate variability, particularly failing to reconstruct the warm periods of the last 10,000 years. These periods recurred roughly every 1,000 years and included the well-known medieval warm period, the Roman warm period, and generally extended warm periods during the Holocene optimum. These past periods were even warmer than the present, despite lower CO2 concentrations than today, and are linked to millennial cycles of solar activity. Who should we listen to? Shall we discuss it? First and foremost, proponents of imminent climate catastrophe should confine their claims to the possible extinction of the human species, rather than the death of the entire planet and biological life in general. Our Earth has been around for about 4.5 billion years and has witnessed climate changes of such magnitude that the current one, assuming it's real, resembles the bite of a microscopic fly. No, the Earth cannot die or fall ill due to human activities. Let's not fool ourselves. We may believe we are powerful and invincible, but we are utterly at the mercy of natural phenomena, to which our presence means next to nothing. Let's consider the magnificent evolution of dinosaurs who thrived for around 180 million years, only to be devastated by the impact of a mere 10-kilometer diameter asteroid. Even worse would be the effects of a standard explosion of a giant star at a distance not too far from our Sun. No, the Earth is not dying, nor is it ailing. It continues its incredibly adventurous existence, never identical to itself, and ready, if necessary, to nurture life once again, something it has done several times before. In fact, Earth's recent past has revealed cycles of substantial fluctuations in average global temperature. The most evident proof is found in glaciations, which seem to have occurred approximately every 100,000 years. Between glaciations and even during them, notable short-term variations have persisted, capable of entirely altering the conditions under which life could survive. In essence, until about 10,000 years ago, glaciations affected Europe at intervals of several thousand years within the overarching 100,000-year cycle. Our lives literally revolve around cycles, sequences of events that repeat in the same order. There are hundreds of different types of cycles in our world and in the universe. Some are natural, like the change of seasons, the annual migrations of animals, or the circadian rhythms that govern our sleep patterns. Others are human-made, like the planting and harvesting of crops, musical rhythms, or economic cycles. What could have generated the altercation between glaciations and thawing on Earth? The answer emerged in the early 20th century from the work of Serbian mathematician Milankovic. Through his studies, he was convinced that the entire cycle of major glaciations over the past millions of years could be described by considering that the Sun, Earth, and other planets are not perfect billiard balls moving in perpetually identical orbits and rotating in the same manner. Everything changes in the universe. Everything is in a constant state of becoming. Specifically, Earth's orbital path is currently nearly circular with an eccentricity of around 0.0167. However, that nearly implies that the difference between aphelion and perihelion is approximately 5 million kilometers. Not only that, in a cycle of about 92,000 years, the eccentricity of Earth's orbit can vary up to a value of 0.058 due to gravitational interactions with other planets, resulting in a difference between aphelion and perihelion that can extend up to 17 million kilometers. Another significant variation is the tilt of Earth's rotation axis to the plane of the ecliptic, currently at 23.4 degrees, which oscillates from 22.5 to 24.4 degrees in approximately 41,000 years. The third major variation involves the orientation of the axis, caused by the phenomenon known as the precession of the equinoxes. This leads to the shifting of the equinox line over time, rotating clockwise and completing a full 360-degree cycle in about 25,800 years. Consequently, Earth assumes opposite inclinations about every 12,900 years concerning the direction of fixed stars. These astronomical cycles influence the amount of solar energy that reaches Earth during different seasons and latitudes. For instance, when Earth's axis is more inclined, the temperature differences between seasons become more pronounced, with a less inclined axis results in more uniform seasons. Additionally, orbital eccentricity brings about variations in the total amount of solar energy Earth receives throughout the year. The combined effects of these cycles can lead to significant changes in Earth's climate. When the variations synchronize in such a way that the solar energy is concentrated in the northern hemisphere during summer months, warmer periods known as interglacial periods can occur. During these times, glaciers retreat and sea levels rise. Conversely, when variations lead to reduced solar energy in the northern regions, glacial periods can take place, characterized by extensive ice coverage and lowered sea levels. In this regard, it's crucial to understand that the alternation between glacial and interglacial periods is dictated by seemingly minor temperature variations. Consider that the average temperature during a glacial period is only 4 to 6 degrees lower than the average temperature during an interglacial period. Nevertheless, the observable effects are striking. During glacial periods, life on Earth becomes rather inhospitable. Thick ice sheets, much like those present at the poles today, extend over large portions of the Earth's hemispheres, covering much of North America and Europe, as well as parts of Asia and South America. With a greater amount of water stored in glaciers, sea levels significantly decrease. It is estimated, for instance, that during the last glacial period, the average sea level dropped by approximately 120 meters, transforming the Baltic Sea into a lake or turning the United Kingdom into a peninsula inhabited by mammoths and massive hairy rhinoceroses. During interglacial periods like the present one, on the other hand, the climate becomes considerably milder. Northern Europe largely frees itself from ice and sea levels rise. The concentration between Milankovic cycles in Earth's climate has been demonstrated through the analysis of climatic data and geological evidence. Ice layers, marine sediments, and carbonate deposits in caves contain valuable information about climate variation over millennia, which can be compared to astronomical cycles. And thus, over the past 2 decades, Milankovic's theory has become the ultimate bastion against the thesis of global warming attributed to human activity. With limited success, it must be admitted, because, although absolutely proven, the theory of cycles by the Serbian mathematician can only account for long-term climatic changes, those brought about by major glaciations interspersed with periods of thousands of years. Thus, proponents of human-induced climate change who are propagating the idea of warming that they claim has risen in a few decades have had an easy time countering the deniers' arguments. If an alternative theory to anthropogenic global warming is to be found, Milankovic's cycles cannot provide any assistance. But hold on a moment. Is it really true that in the past there haven't been episodes of climatic changes occurring over a few decades? If that were not the case, one of the fundamental assumptions of the thesis of warming caused by human activity would crumble. What climatic changes could the presence of medieval or even Neolithic humans have triggered? And we didn't choose these 2 historical periods randomly. Do you remember the so-called Iceman? Etsy, as he was nicknamed by the discoverers, who lived 5,000 years ago and whose mummified remains were found in 1991 amidst the thawing ice of the Italian Alps at an altitude of around 3,200 meters. Was Ötzi a hunter, a shepherd? Well, it's hard to say, but he certainly wasn't a mountaineer climbing to those altitudes. What do you think? And indeed, there's something strange about this story. Think about it. 10,000 years ago, the Alps were still covered in ice amid a glaciation. Yet just a few centuries later, there was a Neolithic villager already at 3,200 meters altitude, pursued by someone who managed to kill him with an arrow in the back. Well, it's difficult for us to imagine that Ötzi lost his life in the snow and ice. Much more likely, he closed his eyes forever in an environment where a sudden warming period had already cleared those altitudes of snow. This means that by 3000 BC, a tremendous thaw had already occurred, allowing people to move freely from Austria to Italy at very high altitudes. A thaw certainly larger than today's, and moreover, it happened in a very short time. Blaming humans for that as well? Hard to believe, isn't it? And then, how do we explain the subsequent rapid drop in temperatures that must have occurred, causing Ötzi's remain to be covered by ice until our days? So it's not true that short-term climate variations don't exist. Earth's entire history is literally filled with them, and they all occurred entirely naturally, without the aid or blame of human beings. Similar episodes have repeated themselves even in periods closer to our own. It's almost needless to recall the sudden warm period lasting from 1000 to 1300, which allowed the Viking Eric the Red to colonize Greenland and then discover America, or the cold period that disrupted Europe and the entire northern hemisphere from 1645 to 1715, known as the Maunder Minimum. Currently, there's a phase of modest warming, although a few remember that in the 70s, there was talk of unbearable cold about to descend upon the Earth. There were even thoughts of covering the North Pole with coal dust. However, the catastrophists seem increasingly convinced, having won over the favor of the media and politics, that a kind of Armageddon is coming due to human activity. On the other hand, the sun has certainly been experiencing a low level of sunspot activity for some years now, almost completely disappearing, just as it did during that Maunder Minimum, which brought about 70 years of intense cold between the 17th and 18th centuries. And in fact, some scientists speculate that this could be the beginning of a periodic solar event called the Grand Minimum, while others argue that there's not enough evidence to support such a position. During a Grand Minimum, solar magnetism decreases, sunspots appear rarely, and less ultraviolet radiation reaches Earth. Grand Minimum can last from several decades to centuries, just like the Maunder Minimum did. In short, the confusion is significant, even if Al Gore's descendants pretend to be right. So, just to summarize and clarify our thoughts, the situation between the two factions is more or less like this. Milankovic's astronomical cycles explain long-term climate changes quite well, but not short-term ones. Global warming proponents say the changes as rapid as what we're experiencing now have never occurred before, and they blame fossil fuel usage. Climate change skeptics, on the other hand, present evidence of equally rapid climate changes that occurred in periods when human activity couldn't have influenced the environment. So how do we sort this out? Is there something we've overlooked? Perhaps volcanoes with their massive and uncontrollable carbon dioxide emissions. That could be true, but catastrophists turn a deaf ear to this and say, mistakenly, but we'll give them the benefit of the doubt, that there haven't been eruptions violent enough in the past 50 years. Perhaps another major neglected factor is continental drift. There is no doubt that the gathering or parting of continental masses can heavily impact the climate, but these are changes that only occur over tens of millions of years. Is there really nothing else we should consider? Well, it almost sounds ridiculous to say it, but in all this debate, there's not a trace of the influence that the only true energy source of the entire solar system can have on Earth's climate, the sun. Catastrophists, with their tangled mathematical models, have considered it, but have underestimated its role to a paltry 7.5%, trying to attribute the occurrence of short periods of warmth and cold recorded over the past 2,000 years to other causes. Climate change skeptics, however, have relied too heavily on the Milankovic cycles for their arguments. which unfortunately only fit long-term variations and don't account for changes in the sun's luminosity. The sun, in fact, doesn't always shine at the same level of luminosity, but slightly dims or brightens due to the tune of 0.1% during an approximately 11-year cycle. Throughout this period, the sun undergoes various changes in its activity and appearance. Solar radiation levels increase or decrease, as do the amounts of material the sun emits into space and the size and number of sunspots and solar flares. These changes have a variety of effects in space, on Earth's atmosphere, and on the Earth's surface. Until now, the scientific community lacked conclusive evidence of a connection between solar variability and climatic changes. However, a new study from the National Center for Atmospheric Research shows for the first time a correlation between the end of solar cycles and one of the periodic meteorological phenomena that occur on Earth: the transition from El Niño to La Niña, which is the atmospheric shift from warming, El Niño, to cooling, La Niña, of the waters in the central eastern Pacific Ocean. Thus, the study suggests a guiding role of solar variability on the meteorological changes within the Earth system. This connection between solar cycles and ocean currents might also explain the recent peak in warming observed in recent years, exonerating at least in part the anthropogenic activity. But the battle continues. It's a battle where, unfortunately, we don't know who the enemy is. Vast interests are at stake, and from all this, one can derive the bitter impression that even science has been put up for sale to the highest bidder. The Stratospheric Polar Vortex, a term that has often, though inaccurately, gained media attention in recent years, is a seasonal high-altitude atmospheric structure that forms in autumn, consolidates in winter, and dissolves in spring. Its developments and shifts from the vertical axis of polar latitudes are often responsible for sudden changes in tropospheric circulation, variations that, especially in recent years, have led to the abrupt spread of polar air towards mid-latitudes. The polar vortex, as we will see, is a structure present on other planets as well. In the past, it has played a fundamental role in shaping Earth's climatic history, particularly in the last 2.5 million years, characterized by a sequence of recurring glacial periods and shorter interglacial periods. Today, thanks to the whims of the polar vortex, we have the fortune, or misfortune, of occasionally experiencing what the average climate conditions were like during the last glacial minimum. We can temporarily return to the conditions that prevailed on Earth 20,000 years ago. But there's a danger lurking: the possibility that over time, some suggest within a couple of decades at most, the polar vortex might collapse definitively, leading us not to just occasional adventurous cold weeks, but to a permanent ice age. Probable or only possible? Let's try to make sense of it all. You've surely experienced it. This question is mainly directed at those living in intermediate latitudes like the northern United States or northern Europe. You go to bed on a mild autumn night, only to wake up semi-frozen in the morning. The unpleasant surprise comes when you look outside and find your car buried under half a meter of snow and encased in ice. At that point, you probably rush to the TV in search of news, just in time to hear your favorite meteorologist amusingly explain that the cause of your little surprise was the sudden breakdown of something called the polar vortex. Indeed, most people must have heard about the polar vortex for the first time in January of 2014, when temperatures plummeted to threatening levels, in some places even 50 degrees Celsius below zero. Do you remember? The weather conditions were so terrible that even in the harsh state of Minnesota, the governor closed schools to protect children from the cold. But perhaps we don't need to go that far back in time. Even in December of 2022, the United States experienced an exceptionally cold period, with snowstorms and temperatures that led to the deaths of at least 63 people. The same happened in February of 2021, when Texas recorded some of the lowest temperatures in the past 30 years, resulting in the deaths of at least 250 people due to the consequences. In fact, for several years now, seemingly contrary to predictions made by global warming advocates, the United States has been witnessing sudden drops in temperatures during the winter season. And indeed, as that meteorologist mentioned earlier, these phenomena are linked to the Arctic vortex, the extensive low-pressure area that hovers over the North Pole. And while it might have been a novelty for most of us at the time, the polar vortex was anything but new for scientists, who had been studying it for at least 30 years. What is the polar vortex? In meteorology, the polar vortex, also known as the Arctic vortex, is an expansive low-pressure region that remains semi-permanent at higher altitudes above the North Pole. It's present almost continuously, particularly during the cold season, and it's much more extensive than any other low-pressure area. If we consider that low-pressure areas affecting Central Europe can have a diameter of 1,000 to 2,000 kilometers or even more, not exactly small, in this case we're talking about a vortex that covers the entire Arctic Circle, with a center roughly over the North Pole. It can even extend to mid-latitudes, boasting a diameter significantly larger than 5,000 kilometers. The vortex is a structure that primarily develops in the stratosphere, typically between 12 and 50 kilometers in altitude, above the troposphere and tropopause, where major atmospheric processes occur. However, this vortex at higher altitudes often affects the lower layers of the troposphere as well, especially when it's intense, leading to the creation of a tropospheric polar vortex. In meteorology, there's a distinction between the stratospheric vortex and the tropospheric one, which more significantly impacts air masses closer to the ground. Unlike the tropospheric vortex, which is more or less present throughout the year, the stratospheric one typically forms in September, reaches its peak intensity in January and February, and dissipates in April until early May. We can think of this circulation as a massive spinning top, filled with frigid air stationed over the North Pole. It exhibits a two-story structure, much like a house with a ground floor and a first floor. In this case, the ground floor is the troposphere, representing the space that extends from sea level to an altitude of around 10 kilometers, where the meteorological phenomena we often analyze occurs. The first floor, much higher, is occupied by the stratosphere, extending up to an altitude of approximately 50 kilometers, separated from the troposphere by a ceiling known as the tropopause. If we could observe all of this from a point in space situated above the North Pole, we'd see an approximately circular cyclonic region with air masses moving counterclockwise, its edge fringed by more or less pronounced undulations. These undulations in meteorology are also known as Rossby waves. A similar vortex is also present above the South Pole and is referred to as the Antarctic vortex, but we'll revisit that later. But what prevents this vortex from moving or expanding indefinitely? Generally, the Arctic vortex is confined above the pole by so-called warmer jet stream, a swift airflow that acts as a barrier to the Arctic vortex like the rim of a bowl. The cold air at the center is denser, effectively trapped within this bowl of warm air. It doesn't exactly exceed the rim, or at least it usually doesn't. When temperatures in the Arctic rise, parts of the cold wind vortex can reach the edge of the bowl, surpassing the usual confines of the jet stream and reaching continental regions. As has been known for decades, the terrestrial polar vortex is a common feature on almost all planets with a thick atmosphere. Similar cyclones have been spotted around the poles of Venus and even Mars, where the atmospheric density might seem insufficient to generate such phenomena. However, despite a shared origin, that of a gaseous fluid surrounding a rotating celestial body, the forms and sizes of these cyclones markedly differ from Earth's. A notable example is the incredible hexagonal vortex encircling Saturn's North Pole. This unique cloud distortion of the planet was first observed by the interplanetary Voyager 1 probe in 1981, and later by the Cassini probe in 2006. With improving image quality, what initially appeared to be a perplexingly geometric formation transformed into one of the strangest and most celebrated wonders of our solar system, an almost perfectly shaped hexagon, with sides measuring around 13,840 kilometers, longer than Earth's diameter. Traditional explanations fall short of shedding light on the origin of this extraordinary structure. One theory suggests a connection between Saturn's unique rotation system and atmospheric dynamics. However, this idea raises more questions than it answers. How can a gaseous planet possess such extraordinarily orderly and stable winds? And why did these winds form a hexagon rather than a different shape? Another explanation involves the action of atmospheric waves. It's postulated to be the result of the interaction between atmospheric winds and waves in a closed-loop current pattern. But even this theory is intricate and doesn't provide a complete answer. Nonetheless, it's interesting to note how the hexagonal pattern can be seen as a much more geometric form compared to the undulating edge of Earth's polar vortex. Saturn's polar hexagon isn't an isolated case. Similar structures have been discovered on other gas giants like Neptune and Jupiter. This suggests that there might be a universal astrophysical mechanism that we still don't fully comprehend. Even Saturn's south pole features a large vortex at its center. However, unlike the North Pole, the Hubble Space Telescope has shown us that there's no particular or persistent cloud formation at its south pole, let alone a hexagonal one. Turning back to our home issues, the polar vortex might seem like a fairly reliable natural system for regulating each hemisphere's climate. In practice, though, it doesn't work that seamlessly. For starters, the vortex's edge, delineated by jet streams, isn't circular but wavy, with protrusions where cold air overflows and descends in latitude and indentations where warm air from lower latitudes attempts to approach the pole. Moreover, the high-speed winds that constitute the polar vortex's barrier can vary in intensity from time to time. If these winds weaken too much, it can distort the vortex and render its boundaries even more irregular, resulting in the leakage of pockets of frigid air. The air that spills beyond the pole's edges is warmer than typical Arctic winds, yet it remains bitterly cold. This warmth could still induce intense snowfalls like those recently experienced in Texas, which lacks mountain ranges for protection, or Europe 2 years ago. But speaking of which, why does the frigid air overflowing from the vortex's bowl cause havoc in Canada and the United States, but not in Europe? North America and Europe share similar latitudes. For instance, New York's latitude is comparable to that of Naples. Nevertheless, it's rare for both continents to be hit simultaneously by cold waves, and such winter phenomena are much more frequent and intense in North America. The reasons for these disparities are manifold. Firstly, although Europe can also be influenced by the polar vortex, the air that reaches it passes over the North Atlantic rather than Canada. Generally in winter, air over land masses is colder than the air above oceans, especially north of Europe due to the warm Gulf Stream. This stream is the main reason why the climate in Northern Europe is milder than that of Canada and North America in general. Conversely, the North American coasts are affected by the influence of cold ocean currents. In contrast, Europe can also rely on the Gulf Stream and the Mediterranean Sea, another heat reservoir. Another reason why North America is more exposed to cold air from the north is related to mountains. The Rocky Mountains, stretching from north to south from British Columbia, Canada to New Mexico, USA, do not act as a barrier to northern winds. Instead, they help channel these winds towards the east. In Europe, the primary mountain range, the Alps, runs latitudinally, serving as a barrier to cold air from the north and contributing to Italy's mild climate. The Ural Mountains, dividing European Russia from Asian Russia, are oriented longitudinally. Despite this, they also play a role in blocking cold air, particularly the frigid mass from Siberia, the nearest major cold continental expanse. However, Siberia is much farther from Europe than the distance between northern Canada and the United States, which is why it doesn't consistently influence the continent's weather conditions. Of course, the question everyone is asking, and you might be too at this point, is the polar vortex influenced by climate change? Supporters of global warming theory emphasize that rising temperatures can indeed contribute to distortions in the polar vortices, and consequently to sudden cold spells. The explanation could lie in the fact that increasing amounts of Arctic sea ice are melting during the summer months. As ice melts, the Arctic Ocean warms and releases excess heat during the winter. Since this warmth somehow reduces the contrast between Arctic air and the atmosphere further south, it weakens the winds that form the barrier between these regions. This, in turn, weakens and disrupts the polar vortex. This hypothesis is backed by data from the last decade, showing that the vortex has a stronger tendency to weaken in years when a significant portion of Arctic sea ice is accelerating its disappearance. Not everyone, it should be noted, supports the idea that changes in Arctic sea ice can influence the stability of the polar vortex to this extent. But if true, it would indeed be concerning because the amount of Arctic sea ice varies from year to year, and in recent years it has been decreasing at an increasingly rapid pace. If Arctic ice were to melt at an even more frantic pace, fresh water would flow in greater quantities into the Atlantic, altering its salinity and significantly disrupting the famous conveyor belt mechanism that enables the Gulf Stream to warm Northern Europe and North America. This could lead to a serious worsening of the climate in the Northern Hemisphere, along with changes in air circulation in the Southern Hemisphere. Moreover, if polar ice caps expand, the albedo effect of sunlight reflecting off the white ice could further lower global temperatures. If this trend continues, it could lead the Arctic polar vortex to collapse in on itself. This could create all the necessary conditions for a small ice age to take hold in the Northern Hemisphere. It's a paradox, as we might have to face the reality that global warming could bring about a drastic temperature drop, not just in the winter months. In short, dear friends, it seems that the environmental future of our planet remains wide open. Perhaps the best approach is to avoid anything that could set in motion climate mechanisms we still understand very little about. What do you think? After years of praying to all the saints in heaven for a few drops of rain, the inhabitants of California found themselves unexpectedly grappling with devastating floods brought by Tropical Storm Hillary last August, which also hit Mexico, Arizona, and Nevada. The deluge triggered by Hillary caused widespread flooding and torrents of debris, with mudflows, boulders, and trees destroying homes and businesses and engulfing motorists. To put it into perspective, the Desert Death Valley received more rain in one day than it typically gets in a year. This was absolutely extraordinary because hurricanes rarely hit California. The first one struck its shores only in 1939, and the last one occurred in 1997, more than 25 years ago. However, one thing is certain: most of the storms that have reached the Golden State, as California is called, have occurred when another cyclical force of nature known as El Niño was in full swing. El Niño is not a new phenomenon, and its study has evolved over time to the present day. It's not an ocean current or one-time nature's whim. El Niño is a cyclical event capable of altering the climate and many other parameters worldwide. According to experts, following the initial signs also reported by the Copernicus mission monitoring system, a complex Earth satellite observation program launched in 1998 by a consortium of space agencies, we can now say that El Niño is returning. And it's likely to be a grand return because its disruptions could combine with the ongoing climate change. The fear in particular is that a very strong El Niño event in 2024 could make it the hottest year ever recorded on our planet. El Niño is a climatic phenomenon that occurs every few years in the Pacific Ocean. It is characterized by abnormal warming of the surface waters off the western coast of South America, which causes changes in atmospheric circulation and affects the climate in many regions of the world. El Niño can lead to droughts, floods, storms, fires, and other extreme weather events. Many years ago, this phenomenon was less violent because it occurred on a planet with lower temperatures and not yet deteriorated by the climate crisis. Now the story is different. We can't expect new heat records, although it's difficult to predict what will really happen. But how does El Niño form, and what are its consequences? To understand this, we first need to know the standard conditions of the Pacific Ocean. Under normal conditions, the trade winds, the ones that pushed Christopher Columbus's ships from Europe to America in the Atlantic, blow from east to west, pushing surface waters towards Asia and Australia. This creates a pressure difference between the two sides of the ocean, higher pressure in the east and lower pressure in the west. This difference strengthens the trade winds, which in turn pushes even more water westward. This creates a circular current called the Walker Cell. The Walker Cell has two main effects. On one hand, it cools surface waters in the east, promoting the upwelling of deep, nutrient-rich waters that support marine life and fishing. On the other hand, it warms surface waters in the west, creating a warm water mass called the warm pool, which extends from Indonesia to the central Pacific Islands. This warm water mass heats the air above it, creating clouds and rain. However, every now and then the trade winds weaken or change direction, allowing the mass of warm water to shift eastwards. This marks the beginning of El Niño. El Niño disrupts the Walker Cell, reducing the pressure difference between the two sides of the ocean and further weakening the trade winds. Warm water spreads towards South America, suppressing the upwelling of deep and nutrient-rich waters, leading to a decrease in marine life and fishing. So one might wonder, why be concerned about a phenomena of local significance that only affects the west coast of South America? Unfortunately, things are not quite so. It is now established that El Niño has global effects, altering atmospheric circulation patterns and influencing the climate in other regions. For example, El Niño can lead to milder winters in North America and Europe, but also more storms in California and the Gulf of Mexico. El Niño can intensify hurricanes in the eastern Atlantic while reducing them in the western Pacific. Additionally, El Niño can impact agricultural production, human health, biodiversity, and the economies of many countries. Furthermore, the tropical Pacific Ocean is so vast that a surface temperature increase of just 1 or 2 degrees is more than sufficient to disrupt the global climate. A slightly warmer ocean evaporates more water, heating the atmosphere and fueling tropical storms. Convective movement, a way heat is transferred, typical of fluids, then carries this additional energy towards cooler regions to the north and south on both sides of the equator. The Earth's rotation also spreads this energy towards the east. The net result is a widespread redistribution of heat and moisture. In climatic terminology, El Niño is an excellent example of the teleconnection of global weather systems. Before moving on, don't forget to subscribe to our channel if you haven't already. Make sure to hit the notification bell so you don't miss out on our daily videos. The warm current of El Niño can typically last from 9 to 12 months, but it's not uncommon for its cycle of activity to persist for up to 18 months. It usually peaks between December and February, but can occur at any time of the year. El Niño was named in the 19th century. At that time, fishermen in northern Peru noticed that almost every year, around the end of December near Christmas, there was a rise in seawater temperature. They attributed this warming to the arrival of a warm ocean current, which they named the El Niño current, in reference to the child Jesus. El Niño is Jesus in Spanish. For them, and still today, it's a matter of economic survival. The vast, gleaming shoals of anchovies on which their livelihood depends prefer colder waters and disappear when El Niño arrives. However, beware. El Niño is not an isolated event, but part of a natural cycle called the ENSO, El Niño Southern Oscillation, which alternates between warming, El Niño, and cooling, La Niña, phases of the Pacific Ocean. La Niña is the opposite of El Niño. It occurs when the trade winds are stronger than usual, pushing more cold water eastward and more warm water westward. La Niña has climatic effects opposite to those of El Niño. For example, La Niña can cause colder winters in North America and Europe, but also more rain in Indonesia and Australia. What perhaps hasn't been emphasized enough when discussing global warming in recent years is that the values recorded in 2022 and 2021 are very close to absolute records, but occurred in years cooled by La Niña, and they are still warmer than years marked by El Niño, even very recent ones. So, El Niño is indeed a complex and fascinating phenomenon that shows us how climate results from a delicate balance between the ocean and the atmosphere, and how variations in one part of the world can have repercussions in another. El Niño also challenges us to better understand the mechanisms that regulate climate, and predict its future changes so that we can adapt and mitigate its negative impacts. But why are we telling you all this? The reason is simple. According to hundreds of experts, in 2024, the world could witness an unprecedented climate event that could have catastrophic consequences for the Earth's climate and life. According to the latest forecast, 2023 and especially 2024 could see a very strong El Niño event, potentially setting a record for global average temperatures and bringing the planet closer than ever to a warming threshold that scientists and policymakers warn could be potentially harmful. According to some estimates, 2024 could be the first year when the global temperature exceeds 1.5 degrees Celsius above pre-industrial levels, a threshold considered critical to avoiding the most severe impacts of climate change. This means that the world could experience irreversible effects such as polar ice melting, sea level rise, ocean acidification, biodiversity loss, increased infectious diseases, and reduced food security. Furthermore, the strong El Niño event could alter long-term climate patterns, changing the distribution of energy between the tropics and polar regions, influencing ocean thermohaline circulation, and modifying biochemical cycles of carbon, nitrogen, and water. These effects could have repercussions on biodiversity, agriculture, drinking water, human health, and global security. The catastrophic consequences of surpassing the 1.5 degrees Celsius threshold are numerous and interconnected. Some of the key ones are the melting of polar ice in high-altitude glaciers, resulting in sea level rise and the loss of habitat for many animal and plant species. It is estimated that with a temperature increase of 1.5 degrees Celsius, sea levels could rise by about 0.4 meters by 2100, while a 2 degree Celsius increase would result in a 0.6 meter rise. This would put coastal populations and infrastructure at risk, exposing them to phenomena such as erosion, saline intrusion, flooding, and storms. Ocean acidification occurs when carbon dioxide absorbed by the water forms carbonic acid, lowering the ocean's pH. This process harms marine organisms that form calcium carbonate shells or skeletons, such as corals, mollusks, and crustaceans. Loss of terrestrial and aquatic biodiversity occurs when species fail to adapt to climate changes and lose their habitats or food sources. With a temperature increase of 1.5 degrees Celsius, 6% of insects, 8% of plants, and 4% of vertebrates could lose more than half of their climatic range by 2100. With a 2 degree Celsius increase, these percentages would rise to 18%, 16%, and 8% respectively. Increased infectious diseases occur when climate change promotes the spread of pathogens or vectors such as mosquitoes or ticks. According to a recent study, a temperature increase of 1.5 degrees Celsius will have catastrophic and irreversible health consequences, including the rise of infectious diseases. These diseases can affect both humans and animals, causing deaths, disabilities, and healthcare costs. Reduced food security occurs when climate change reduces the availability and quality of food, both directly affecting crops and livestock and indirectly affecting supply and distribution chains. With a temperature increase of 1.5 degrees Celsius, global wheat production could decrease by 2%, while a 2 degrees Celsius increase could lead to a 7% decrease. Similarly, global maize production could decrease by 7% with a temperature increase of 1.5 degrees Celsius, and 12% with a 2 degrees Celsius increase. This would jeopardize food security and nutrition for millions of people. Another grim consequence of a particularly strong El Niño is the increase in diseases. Viruses replicate more rapidly in vectors like mosquitoes as temperatures rise. Mosquitoes also bite more frequently in the heat. Heavy rains create more breeding sites for insects, as does drought when people collect more water in accessible containers. Research compiled by the World Health Organization found that drought conditions associated with El Niño over 2 decades increased malaria cases in Colombia and Venezuela by more than a third. A strong El Niño in 1997-1998 was linked to major malaria outbreaks in Ethiopia, Kenya, and Uganda. This year's heavy rains and floods have exacerbated Peru's worst-ever dengue epidemic, overwhelming hospitals in the north. Flooding can lead to poor hygiene, causing an increase in diarrheal diseases. Displacement and overcrowding following a disaster exacerbate these epidemics. If the Horn of Africa were truly soaked in rain, a surge in cholera cases is likely. Malnutrition worsens vulnerability to diseases, especially among the young and the elderly. Save the Children, a charity, argues that the upheaval brought by the 2015-2016 El Niño left an additional 6 million children malnourished worldwide, 3 times the number affected similarly by COVID-19, and the pandemic has left healthcare services overloaded and weakened. These aren't just a few examples of the catastrophic consequences that could result from exceeding the 1.5 degrees Celsius global warming threshold in 2024. These are scenarios we can't afford to face, neither environmentally nor socially and economically. That's why it is urgent to take action now to reduce greenhouse gas emissions and limit global warming to a maximum of 1.5 degrees Celsius. Only then can we safeguard our planet and our future. How can we deal with El Niño? El Niño is a natural phenomenon that we cannot prevent or control. However, we can try to monitor its development and prepare for its effects both individually and collectively. To monitor El Niño, we can use various observation and prediction tools, such as satellites, ocean buoys, climate models, and statistical indicators. These tools allow us to track the evolution of oceanic and atmospheric conditions and anticipate the impacts of El Niño on different regions of the world. To prepare for its effects, we can adopt various adaptation and mitigation measures, such as water resource management, crop and livestock protection, disease and disaster prevention, international cooperation, and humanitarian assistance. These measures enable us to reduce the vulnerability of populations and ecosystems to the negative effects of El Niño and take advantage of the positive opportunities it can offer. However, these actions are not sufficient if we do not address the root causes of climate change, which makes El Niño more frequent and intense. To do this, we must reduce greenhouse gas emissions and promote sustainable and resilient development. Only in this way can we prevent events like El Niño from becoming increasingly dangerous for the future of the planet and humanity. Regardless of how it turns out, what is certain is that we will not be able to cope with the nightmarish temperatures we will face next year. For those, there is nothing left to do. It will be a hellish scenario.